Good morning, children. In unit electromagnetic induction, we have next topic is Lenz'S Law. According to Lenz'S Law, the polarity of the induced EMF is such that it always opposes the motion of bar magnet. Yes. Suppose north pole of the magnet is moving towards the coil like this. Due to the motion of the bar magnet, north pole is moving towards the coil. Then magnetic flux will be changes in the coil. Therefore, induced EMF will be produced. The direction of the induced EMF is such that, or induced current is such that it is in the anti-clockwise direction. If it is in the anti-clockwise direction, therefore we can say that north pole will be produced on the face of the loop which is closer to the north pole. Now you can say this is the direction of induced current. So the polarity is north here. So this north will repel the north. So we can say that this north pole opposes the motion of the bar magnet. In the second case, if the south pole is moving towards the coil here, this is south pole, this is north pole, south pole is moving towards the coil, this is coil here, then we can say induced EMF will be produced and the direction of induced EMF that will be clockwise like this. We can write here this is clockwise direction. If it is clockwise direction, then the face of the loop which is closer to the south pole, then south pole will be formed which opposes the motion of the bar magnet. So according to the Lenz'S law, the induced EMF, or you can say the direction of the induced EMF in the loop is such that it always opposes the motion of the bar magnet. Suppose south pole is moving away from the magnet. If the south pole is moving away from the magnet, then we can say here that this is south pole, this is north pole. South pole is moving away from the coil. Now, due to the change in magnetic flux, EMF will be induced and the direction of induced EMF that will be anti-clockwise. So if the direction is anti-clockwise, so we can say that north pole will be formed. So this north will attack the south pole. So therefore this north pole attack the south pole, so it opposes the motion of the bar magnet. Here in the case 1, north pole opposes the motion of the bar magnet. This south pole opposes the motion of the bar magnet by repelling the south pole. And in the third case, the north pole is formed which attack the south pole, so it opposes the motion of the bar magnet. So we can say that the induced EMF produced in the coil always opposes the motion of the bar magnet. Next topic is method of producing motional EMF. First, by the motion of a bar magnet. Let the rectangular coil KLMN is placed in the uniform magnetic field, capital B. Let L is the length of the coil, rectangular coil, V is the velocity. Now we can say the coil is moving outward from the bar magnet, from the magnetic field. This is the breadth X which is coming out from the magnetic field. So this is length L. So this is the area which is coming out from the magnetic field. So now we know magnetic flux phi is equal to, this is equals to B into A. Now area is length into breadth, L into X. So we can say phi is equal to minus B into L, B, L into X. Why the negative sign is here? Because the area is decreasing in the magnetic field. So negative sign will be here. According to Faraday's laws of EMI, E is equal to minus d phi upon dt. We can write here minus d by dt of phi. This is minus B into L into X. Minus minus will be positive. So we can write here B into L. This is dx upon dt. Now we can write here dx upon dt, displacement upon time, this is equal to velocity. So we can write here E is equal to B into L into V. So the induced EMF in the rectangular coil, that will be E is equal to B into LV. According to Ohm's law, we can calculate current. I is equal to E by R. So the value of E is BLV upon R. So the current will be BLV upon R. Second method is by rotating the conducting rod in a magnetic field. Let a conducting rod of length L, it is rotating in a magnetic field. In a time t, the conducting rod makes an arc PQ. It makes an angle alpha with the center. Omega is angular velocity. We know angle theta is equal to arc upon radius. So angle theta is equal to arc upon radius, that is OP. So alpha is equal to, we can write here, alpha is equal to PQ upon, this is L. So we can write here PQ is equal to alpha into L. So this is arc PQ. Now area of a sector POQ, this is equal to, area is, we can write here half into radius into arc. Area is half into radius. Radius is L into arc PQ, that is alpha into L. So area is half into alpha into L square. Now magnetic flux phi is equal to B into A. So phi is equal to B into A is half into alpha into L square. According to Faraday's law, we can write here E is equal to d phi upon dt. We can write here d by dt of phi, this is half into B into alpha into L square. Now we can write here half into B L square into, we can write here d alpha upon dt. D alpha upon dt here is angular velocity. Omega is d alpha upon dt. So we can write here A is equal to half into B L square into omega. This is the relation for the conducting rod rotated in a magnetic field.